Welcome back to the deep dive. Today we're conducting something of a demolition experiment.
A demolition experiment on a cosmic scale, effectively.
Right. We're taking the grand architecture of our solar system, finding what seems to be the most critical load-bearing wall, and then we're just going to knock it down.
Just to see what happens to the roof.
Exactly.
We're engaging in what astrophysicists would call a counterfactual simulation.
Usually when we talk about space, we're focused on what's there. You know, the stars, the planets, the asteroids.
The habitable zones, all of it.
But today, we're talking about what happens when something massive, something absolutely fundamental to our cosmic neighborhood, simply ceases to exist. We're asking, what if Jupiter vanished tomorrow?
It's a scenario that, it sounds like pure science fiction. Or maybe a horror story for anyone who studies orbital mechanics.
I'd imagine so.
But stripping away a major component of a system is actually one of the most effective ways to understand how that system truly works.
Right. You don't really know what a keystone does until you pull it out of the arch.
And you watch all the other stones start to slip.
So let's set the stage for this. We're using the Eclipse Master Knowledge Core and the Planetary and Cosmic Disaster Simulation module to run this whole scenario. Here's the premise. Imagine it's tomorrow morning, a Tuesday, 9:00 a.m. Astronomers are at their telescopes. The Deep Space Network is tracking data from the Juno spacecraft orbiting Jupiter. And then just silence.
Absolute signal loss.
Yeah.
And we need to be really precise about what silence means here.
Okay.
We aren't talking about the planet exploding. An explosion leaves debris. It leaves mass. It leaves energy.
Right. If it exploded, we'd have a completely different and probably much messier set of problems on our hands. A giant cloud of superheated gas expanding outward.
Exactly. In this simulation, we're executing a pure deletion event.
The deletion event.
We are, for the sake of the thought experiment, violating the first law of thermodynamics, the conservation of mass and energy.
Just to see what the gravitational architecture does when you remove the anchor.
Precisely. The mass of Jupiter is 1.898 times 10 to the 27th kilograms. And in our scenario, poof, that mass is instantly deleted from the universe.
I want to pause on that number because scientific notation, it just tends to numb the brain. 1.898 times 10 to the 27th kilograms?
It's an impossible number to visualize directly. I mean, truly.
I was trying to do the math on this before we started just to get some kind of handle on the scale.
And
if you took our planet, Earth, everything, the core, the mantle, the oceans, every city, the whole thing, and you put it in a bucket, you would need 318 of those buckets to equal the mass of Jupiter.
That's a very good way to picture it. Or think of it this way. Jupiter is 2.5 times more massive than all the other planets in our solar system combined.
All of them?
All of them. Saturn, Uranus, Neptune, Earth, Venus, Mars, Mercury.
Even the asteroid belt, all the moons.
Throw it all in. Roll them all into a single giant ball, and Jupiter is still more than double that mass.
It's a beast.
It is the dominant gravitational force in our system. Second only, of course, to the sun. In fact, you'll often hear astronomers refer to Jupiter as a failed star.
A failed star. I've heard that term. And that's because it's mostly hydrogen and helium, right? The same stuff as the sun.
Precisely. Compositionally, it's very, very similar to a star. If it had been about, say, 80 times more massive when it was forming,
80 times.
the pressure and temperature in its core would have been high enough to ignite nuclear fusion. It would have lit up. We'd be living in a binary star system.
There's suns in the sky.
Can you imagine? But it didn't quite make that weight class. However, just because it didn't ignite doesn't mean it's passive. It is the gravitational foreman of the solar system.
Okay, I like that analogy.
The sun is the CEO. It holds 99.8% of all the mass. But Jupiter is the one on the ground, managing the workforce.
So the question we're diving into today is, if you fire the foreman, if you just delete that mass, what happens to the workers? Does Earth just fly off into deep space? Do we freeze? Does the asteroid belt suddenly decide to pay us a visit?
Well, there's a very common belief, one that's repeated a lot in popular science, that Jupiter is our cosmic shield.
Right.
That it acts like a giant vacuum cleaner, sucking up asteroids and comets that would otherwise be on a collision course with Earth. So the immediate assumption is, well, if the shield is gone, we're sitting ducks.
I've definitely heard that. The whole idea that without Jupiter, we'd have been wiped out by a dinosaur killer level asteroid a long, long time ago, that it's our benevolent protector.
And we are absolutely going to test that. We'll look at the cosmic shield theory versus the much more complicated reality of orbital mechanics. But we're also going to look at something more subtle and and perhaps more terrifying in the long run.
And what's that?
The gravitational web that holds everything together. Because when you remove a player as big as Jupiter, you aren't just changing the scenery, you're breaking the rules of the road.
So let's start with the basics of that web. We've established the sheer mass of the thing. Why does that specific mass matter so much in the context of where Earth is right now?
It all comes down to Newton's law of gravitation, fundamentally. But we need to look at it a bit deeper than, what you might remember from high school physics.
Okay.
Gravity is a function of two things, mass and distance. The more massive an object, the stronger its pull. But gravity is also a field. It's a texture in space-time.
The classic bowling ball on the trampoline analogy.
Exactly. The sun is a massive bowling ball in the center, creating this deep well. Earth makes a little divot. Jupiter creates a massive canyon of its own. Now, here's the nuance that most textbooks kind of speak over.
What's that?
The sun is not a stationary anchor.
The sun moves.
The sun wobbles. Jupiter is so incredibly massive that it actually yanks the sun around. The two of them, the sun and Jupiter, they orbit a shared center of gravity. It's called the barycenter.
Okay, let's unpack this. A barycenter.
Imagine two ice skaters holding hands and spinning around. If one is huge and one is tiny, the huge one barely moves, right? The tiny one just flies around them.
Sure.
But if they're both heavy, they both spin around a point that's somewhere in between them. That point is the barycenter.
And for the Earth and the sun, that point is basically inside the sun because the sun is so much bigger.
Correct. We're a gnat compared to the sun. The barycenter is deep inside the sun's core. But Jupiter is a heavyweight.
So it's a different story.
A very different story. The center of gravity between the sun and Jupiter is actually outside the surface of the sun. It's at about 1.07 solar radii from the center.
Wait, so you're telling me the sun is technically orbiting a point in empty space?
That's exactly right. The sun is performing this little pirouette around a point in space because Jupiter is pulling on it so hard it creates this constant spiral motion. So the moment you delete Jupiter,
that pirouette stops.
Instantly. The skater lets go of their partner. The sun experiences a kind of gravitational snapback. The momentum of the whole system has to be conserved, so that motion changes.
Okay, so let's hit the button. Simulation is running. Jupiter vanishes. It's gone. What happens in that first hour? Are we immediately flying out of orbit? Do I need to grab my winter coat because we're leaving the habitable zone?
This is where the physics of information speed comes into play. Gravity travels at the speed of light.
Which is incredibly fast, but it's not instant.
Exactly. It takes light, and therefore gravity waves, about 43 minutes to travel from Jupiter's orbit to Earth. It varies a bit depending on where we are in our respective years, but that's a good average.
So Jupiter vanishes, and for the next 43 minutes, Earth literally doesn't know that it happened.
We are orbiting a ghost. The gravitational field from Jupiter is still rippling toward us. But once that wave passes, nothing dramatic happens to us instantly.
Nothing, really.
Visually, if you were looking up at the night sky with a telescope, you'd just see Jupiter disappear, blink out of existence. But physically, here on Earth, you wouldn't be thrown against a wall, the ground wouldn't shake.
But you just said the sun snaps back, that the barycenter shifts.
It does. But we have to remember the scale here. The sun is still 1.9 times 10 to the 30th kilograms. It is 1,000 times more massive than Jupiter.
So it's still in charge.
Overwhelmingly. The sun's gravity is what holds Earth in its orbit. We are swinging around the sun, not Jupiter. So if Jupiter vanishes, the sun is still holding onto us tight. We don't fly off into the void.
Okay, so not ejected from the solar system. That's good news. We stay near the heat source.
We do. In the immediate aftermath, hours, days, even weeks, the solar system would appear to continue on almost normally. The planets keep orbiting, the Earth keeps spinning, the illusion of stability would hold.
The illusion of stability. I don't like the sound of that. That implies that underneath the surface, things are starting to break.
Well, this is where we move from the immediate effects into the medium term. Now we're talking months and years. That silence after the disappearance is deceptive. Because while the sun dominates the gross structure of the system, Jupiter handles all the fine-tuning.
The foreman is gone, so the workers start slacking off.
Well, they start running into each other. Jupiter exerts this constant rhythmic tug on everything else in the system. And this creates something we call orbital resonance.
I want to dig into that. Resonance. It sounds like a musical term.
And it's a perfect analogy. Think about pushing a child on a swing. If you push at the exact right moment every single time in resonance, The swing goes higher and stays in a perfect rhythm.
But if you just push at random time,
The energy cancels out, the swing goes nowhere. Jupiter pushes and pulls on asteroids, on other planets, even on the sun itself, in a way that keeps them in very specific gravitational lanes.
so it's not just sitting there being heavy, it's actively managing the system.
It is sculpting this system constantly. And the most immediate place we would see the effects of its absence is the asteroid belt.
The big field of rocks between Mars and Jupiter.
Right.
Wow.
Now, in the movies, the asteroid belt is this dense field where you're dodging rocks every second.
Yeah, you can't fly a ship through it.
In reality, the asteroids are very, very far apart. But there are millions of them. And if you look at a map of the asteroid belt, it's not uniform. There are gaps.
Gaps, like empty lanes on a highway.
Exactly like that. They're called the Kirkwood gaps. And they correspond precisely to those resonances we were just talking about. For example, there's a big gap where an asteroid would orbit the sun exactly 3 times for every 1 time Jupiter orbits, the 3-to-1 resonance.
And why is that lane empty?
Because if an asteroid tries to settle in there, Jupiter tugs on it at the exact same point in its orbit, over and over and over again. It pumps energy into that asteroid's orbit until, flick, it gets ejected.
So Jupiter keeps those lanes clear.
It's a no parking zone, enforced by the biggest tow truck in the universe.
Okay, so Jupiter is the tow truck. Now the tow truck is gone.
And the no parking signs are gone with it.
So the asteroids, they just start drifting into those lanes.
Over years and decades, yes, the strict structure of the asteroid belt begins to dissolve. The asteroids are already drifting a bit due to things like the Yarkovsky effect, that's uneven, heating from the sun, and small gravitational nudges from Mars. Without Jupiter there to kick them back out, they drift into the gaps.
And once they're in the gaps,
They don't stay there. The resonances are gone, so they don't get kicked out immediately, but the whole belt becomes fluid. It loses its rigidity. But the real, more immediate danger isn't even the main belt. It's the parking lots outside the belt. We need to talk about the Trojans.
the Trojan asteroids, I've seen these on diagrams. These are the ones that actually share Jupiter's orbit, right?
Correct. And this is a crucial piece of the puzzle that often gets overlooked. Jupiter has 2 massive swarms of asteroids that travel with it. One swarm is 60 degrees ahead of the planet, and the other is 60 degrees behind it.
And they just stay there. They don't crash into Jupiter.
They sit in what we call the Lagrange points, specifically L4 and L5.
Lagrange points. We should probably define that.
A Lagrange point is a gravitational sweet spot. It's a point in space where the gravity of the sun and the gravity of a planet, in this case Jupiter, perfectly cancel out the centrifugal force of motion. It creates a stable pocket, little gravity well.
A celestial parking spot.
Exactly. And Jupiter's L4 and L5 points are absolutely packed. We're talking about thousands upon thousands of asteroids. Some estimates suggest that the total mass of the Trojan asteroids might actually rival the mass of the entire main asteroid belt itself.
Wow. So we have 2 massive clouds of rocks, millions of them just parked in these gravity wells.
And we just deleted the gravity well.
We deleted the parking lot.
And it's catastrophic for that local space. Instantly, the mechanism holding those rocks in L4 and L5 vanishes. Now they're just rocks, moving at orbital velocity with absolutely nothing to constrain them.
So they just disperse.
They derail. They are suddenly on highly elliptical, chaotic orbits relative to where they were. They start crossing lanes of traffic. Some will be flung outward, deeper into space, but a significant percentage will spiral inward.
Inward, towards Mars, towards Earth.
Exactly. This is probably the most immediate danger. Not the main belt that takes a very long time to really destabilize, but the Trojans. You've just kicked over a beehive.
And how long before those bees get here?
Simulation models suggest that within a few thousand years, which is a blink of an eye, cosmically speaking, Earth would see a noticeable spike in impact probabilities.
So we'd be dodging shrapnel from Jupiter's empty parking spots.
We would. And this brings us all the way back to that cosmic shield idea we started with.
Right, the vacuum cleaner theory.
Yep.
If Jupiter is gone, is the shield gone? Are we suddenly going to get hammered by asteroids?
So we need to unpack the myth versus the reality here. Jupiter does act as a shield, in a sense. It does absorb some impacts. The most famous example of this happened in July of 1994. Do you remember Comet Shoemaker-Levy 9?
I do, vaguely. I remember the pictures. It looked like a string of pearls in the sky.
That string of pearls was a comet that had flown too close to Jupiter on a previous pass. Jupiter's gravity, the tidal forces, literally ripped the comet apart. And then, in this spectacular display, The fragments slammed one by one into Jupiter's atmosphere.
The explosions were huge, right? Bigger than Earth?
Massive.
Mhm.
The scars they left on Jupiter's clouds were larger than our entire planet. If that comet had hit Earth instead of being captured by Jupiter, well, we wouldn't be having this conversation. We would be extinct.
So that's the proof. It saved us. It's a shield.
In that specific instance, yes, absolutely. It took a bullet for us. But the simulation data shows it's a double-edged sword.
How so?
Jupiter's also a gravity slingshot. Yes, it throws things out of the solar system, and yes, it absorbs some hits. But it also throws things in.
It slingshots things towards us.
It redirects comets toward the inner solar system just as often as it ejects them. It controls the traffic, but it directs some of that traffic right across our path. Without Jupiter, we lose the shield, but we also lose the slingshot.
So it's less of a shield and more of a chaotic gatekeeper.
A gatekeeper is a very good word for it. It disrupts the Oort cloud comets that fall in from the outer edges of the system. Without Jupiter there, that traffic control system is just gone.
So without the gatekeepers, do we get fewer comets or more?
That is the multi-billion-dollar question. In the short term, say decades to centuries, we might actually see a lull in the number of long-period comets. The slingshot that sometimes throws things at us is broken.
Okay.
But over the long term, without Jupiter to eject those comets coming in from the deep freeze of the Oort cloud, the total flux of comets crossing Earth's orbit changes. We lose our active defense system against the really big, fast-moving objects from deep space.
So boiling it all down, are we doomed? Is it an asteroid rain within a few years?
No. No, we have to be realistic. This isn't a Hollywood blockbuster where the sky catches fire on day 3.
Right.
The timeline for these orbital mechanics is long, very long. We're talking about a slow-motion destabilization. Impact rates might increase, but it would be a statistical change. A slight tick upwards in the probability over centuries, or more likely, millennia.
Okay, so I don't need to build a bunker tomorrow morning.
Not for the asteroids, no. But the asteroids aren't the only things Jupiter is pulling on. We have to talk about the other planets.
Right. Saturn. It's the next biggest giant out there. It's right next door, cosmically speaking.
And Saturn and Jupiter have a very specific, very important relationship. They're locked in a resonance, roughly a 5-to-2 resonance. For every 5 times Jupiter goes around the sun, Saturn goes around almost exactly twice.
They're gravitational dance partners.
The most important dance partners in the whole system, and we just deleted one of them.
Saturn is suddenly dancing alone.
Its orbit would immediately begin to shift. Without that resonant tug from Jupiter, it would likely settle into a different eccentricity, meaning its orbit might become more oval-shaped rather than circular.
Does Saturn changing its dance moves really affect us all the way in here? It feels pretty far away.
Everything affects everything. Gravity has infinite range. It gets weaker with distance, of course, but it never ever reaches zero. If Saturn shifts, it pulls on Uranus and Neptune differently. It pulls on the Earth differently. But the real concern for the inner planets, Mercury, Venus, Earth, and Mars, is the chaos factor.
Chaos. I hear that word a lot in physics. But in this context, we aren't talking about panic in the streets. We're talking about math.
Yes, we're talking about n-body gravitational dynamics.
N-body, as in number of bodies.
Exactly. Newton famously solved the gravity problem for 2 bodies. If you just have the sun and the Earth, the math is perfect. It's a closed loop. You can predict with near-perfect accuracy where Earth will be in 1 billion years.
But the moment you add a third body.
The moment you add Mars or Venus or Jupiter, the math breaks.
It becomes unpredictable.
It becomes chaotic in the mathematical sense. The bodies all tug on each other, and those tiny tugs compound over millions of years. The future outcome becomes hypersensitive to the initial conditions. This is the butterfly effect.
A butterfly flapped its wings in Brazil, and you get a tornado in Texas?
Right. Now, in the solar system, we have something called the Lyapunov time. It's a kind of mathematical horizon. It's the time limit beyond which we simply cannot predict where the planets will be.
Okay.
Currently, for our solar system, that time is roughly 5 to 10 million years.
So even with our best supercomputers, we can't prove that Earth won't hit Venus in, say, 100 million years.
We can't prove it now.
Yeah.
But we know the probability is vanishingly low because Jupiter acts as a massive damper. Its huge mass and stable orbit suppress the little wobbles of the smaller planets. It acts like a heavy anchor chain on the whole system. It keeps the Lyapunov time long.
It extends our horizon of predictability.
Precisely. Now, delete Jupiter. The dampener is gone. The mutual gravitational buzzing between Earth, Venus, and Mars suddenly takes over. They start tugging on each other much more significantly without the boss in the room to drown them out.
The mice start to play.
And the game gets rough very quickly. Simulations show that without Jupiter, the eccentricity of Mercury's orbit starts to pump up.
Mercury's the smallest, so it gets bullied the easiest.
It does. It's the run to the litter. As its orbit stretches, it becomes more and more elliptical. If it stretches too far, there's a non-zero chance it could cross Venus's orbit.
A collision.
A collision is possible, or a gravitational slingshot. Mercury could disturb Venus, which in turn disturbs Earth. We ran one simulation where Mercury is actually ejected from the solar system entirely.
Wow.
But on its way out, it passes close enough to Earth to fundamentally alter our orbit.
And that brings us to the real nightmare scenario. Because if our orbit changes, our distance from the sun changes.
Correct. The Goldilocks zone, the habitable zone where water can remain liquid, is actually quite narrow. If Earth's orbit becomes just 10% more eccentric, because of this chaotic drift, we could spend part of our year significantly closer to the sun and part of it significantly further away.
We'd roast in the summer and freeze solid in the winter.
To a degree that complex biology might not be able to sustain. We aren't talking about needing a heavier sweater. We are talking about oceans potentially boiling and then freezing over year after year.
That's a truly terrifying thought. Planets colliding, oceans boiling, and all because we removed a planet 500 million miles away.
It shows just how deeply interconnected the entire system is. But there's an even more subtle danger that could affect life on Earth much, much sooner than a planetary collision.
What's that?
Climate. And I don't mean CO2 levels. I mean the very geometry of our planet's movement. I mean the Milankovitch cycles.
Okay, let's unpack this. Milankovitch cycles. I've heard the term in relation to ice ages.
That's exactly right. Earth's long-term climate isn't just about our atmosphere. It's driven by how our planet moves through space. There are three main factors. Our axial tilt, which is called obliquity, the shape of our orbit called eccentricity, and the wobble of our axis, like a spinning top, which is called precession.
And these things change over time.
They do. They cycle rhythmically over tens of thousands of years. And these cycles are governed by the gentle, constant gravitational tugs of Jupiter and Saturn.
I see where this is going. Jupiter stabilizes these cycles.
Jupiter and Saturn together keep our orbit relatively circular. But more importantly, let's look at that axial tilt. Right now, Earth tilts at about 23.5 degrees. That gives us our seasons. It wobbles a tiny bit between about 22 and 24 degrees, but not much.
It's stable.
It's stable because of our large moon, largely, but also because of the resonance constraints of the giant planets. Now look at Mars. Mars doesn't have a big moon, and it gets yanked around by Jupiter all the time. As a result, Mars's tilt varies wildly, from 0 degrees to 60 degrees over millions of years.
60 degrees, that's practically lying on its side.
Imagine if Earth did that. If we tilted to 60 or even 90 degrees, the North Pole would point directly at the sun for months at a time. The ice caps would melt instantly. The tropics would become polar regions. The entire planet would cycle between hothouse Earth and snowball Earth.
So Jupiter is basically the thermostat regulator for the entire planet on a geological timescale.
In a very real way, yes. It regulates the orbital parameters that dictate our long-term climate stability. Without Jupiter, and with the resulting chaos in the outer planets that we discussed, Earth's axial stability over millions of years becomes a huge question mark. We could enter a period of chaotic tilt.
It's amazing to think that a distant ball of gas is one of the reasons I can enjoy a predictable spring and autumn.
It is the interconnectedness of the cosmic architecture. You really cannot isolate one part of the system and expect it not to affect everything else.
Speaking of architecture, I want to pivot to the past for a moment. We've been talking about what happens if Jupiter vanishes tomorrow. But reading through the source material on the grand tack hypothesis, it seems like if Jupiter hadn't been there in the very beginning, we wouldn't even be here to have this conversation.
This is one of the most fascinating parts of the Eclipse yard simulation data. The grand tack hypothesis suggests that in the very early solar system, Jupiter didn't just stay put where it is now. It migrated.
Migrated, as in it moved closer to the sun.
Yes. The theory goes that it formed further out, spiraled inward toward the sun, clearing out a massive amount of gas and dusty debris as it went, and then, thanks to a gravitational interaction with Saturn, it tacked, like a sailboat changing direction, and moved back outward to its current position.
And why does that tack matter for us, for Earth?
Because that inward journey essentially cleared the playing field. It scooped up or ejected a huge amount of the raw material in the inner solar system. If Jupiter hadn't done that, there might have been too much material left over in this region.
And if there was too much material,
Earth might have grown too big. We might have become a super Earth.
A super Earth. That actually sounds kind of cool.
It sounds cool, but it's likely not habitable for life as we know it. Super-Earths tend to have crushing surface gravity and thick, choking atmospheres. Or we might have become a water world, a planet completely covered in a 100-mile deep ocean with no land masses at all.
So Jupiter's journey literally sculpted the zone where Earth was able to form.
Precisely. It created the specific Goldilocks conditions that allowed a small, rocky planet like ours to form with just the right amount of water and just the right kind of atmosphere. Without Jupiter's historical influence, Earth as we know it likely wouldn't exist. We are, in a very real sense, the beneficiaries of its ancient gravity.
That puts a whole new spin on the cosmic shield idea. It wasn't just protecting us now, it built our house in the first place.
It was the architect.
I want to take a step back for a second and look at the realism of all this. We started by saying Jupiter vanishes, but physics says that's impossible, right?
Strictly speaking, yes. The law is conservation of mass. Mass cannot be created or destroyed. You can't just delete a planet.
But there are real-world scenarios where a planet could leave, right?
Yes. We call it planetary ejection. It usually happens in the chaotic early days of the solar system's formation, but it's theoretically possible later on. If a rogue star, a star not bound to any system, passed close to our solar system.
A drive-by shooting, gravitationally speaking.
That's a good way to put it. Its gravity could deeply disrupt the orbits. It could, theoretically, grab onto Jupiter and just fling it out into the interstellar dark. Jupiter would become a rogue planet, wandering the galaxy all alone.
And in that scenario, we'd still be here, dealing with the exact aftermath we just spent all this time discussing.
We would, and the process of that ejection would likely be far more violent. The gravitational chaos caused by a passing star powerful enough to eject Jupiter would be a true apocalypse for the solar system, far worse than our clean vanishing scenario.
It really highlights how fragile this whole setup is. We look up at the planets and they seem so permanent, like they're carved in stone up there.
That is the human bias of time. We live for maybe 80, 90 years. Civilization has been around for a few thousand. To us, the stars are static. The planets are fixed points of light. But on a cosmic timescale, the solar system is a dynamic, evolving organism. It's an incredibly delicate clockwork mechanism.
A clockwork where all the gears are made of gas and rock and hold each other in place with invisible strings.
Invisible gravitational balances, that's the key phrase. We rely on forces we cannot see. We rely on a planet 500 million miles away to keep our asteroids in line, to keep our seasons stable, and to keep our orbit nearly circular.
It brings up the anthropic principle, doesn't it?
It really does. The idea that the universe and our specific local neighborhood seems almost fine-tuned for life. If Jupiter was slightly smaller, or slightly closer, or didn't exist at all, we wouldn't be here to talk about it.
We are small creatures, riding a small rock that is balanced by a distant gas giant. It makes you feel incredibly precarious.
It should, but it should also make you feel connected. We are not separate from the cosmos. We are a direct product of its history and its ongoing mechanics.
So if we look at the bottom line here, if Jupiter vanished tomorrow, we don't die instantly. We don't fly into the sun. But the clockwork breaks.
The clockwork breaks. The long-term guarantee of stability completely dissolves. We would enter a new phase of slow-motion chaos. The guarantee of a safe future for Earth over the next billion years evaporates.
It's a sobering thought. We are safe today because of a giant we rarely, if ever, think about.
It reminds us that stability is not the default state of the universe. Stability is a rare and precious equilibrium.
Before we wrap this up, I want to ask you for a final thought. We've covered the physics, the climate, the history, the chaos. What is the one thing you want our listeners to take away from this whole thought experiment?
For me, it comes down to the illusion of isolation. We so often think of Earth as an island. We worry about our atmosphere, our oceans, our borders. But this deep dive shows that Earth, as a habitable system, includes Jupiter. It includes Saturn. It includes the sun. You cannot draw a circle around our planet and say, this is where our environment ends. Our environment is the solar system.
The neighborhood matters.
The neighborhood matters more than anything. And keeping the neighbors happy, or at least keeping them in their established orbits, is absolutely essential for our long-term survival.
Well, let's all hope Jupiter decides to stay exactly where it is. I, for one, am very grateful for our gas giant overlords.
As am I.
Thank you for taking this journey with us. It's been a fascinating and slightly unnerving look at the what if.
It's always a pleasure to break the solar system with you.
And for everyone listening, keep looking up. There's a lot of heavy lifting happening out there in the dark on our behalf.
Perhaps the most extraordinary truth is not that Jupiter protects us, but that life on Earth emerged within a gravitational architecture so delicately balanced that even the disappearance of a distant giant would echo across millions of years.
That's it for this deep dive. We'll see you in the next orbit.